Hey everyone, welcome to lecture 8. We are going to talk about work and kinetic energy today, as you've probably realized. So let's get started here. The first thing I want to say is that there are many different kinds of energy in physics, right? But we're going to talk about translational kinetic energy. So let me say, but the translational kinetic energy of an object of mass m traveling with speed v is given by, and we'll use a big K for this, and it's just going to be 1/2 m v squared. Okay. So what do I always talk about immediately after I define something, right? The dimensions. So let's briefly discuss the dimensions of the kinetic energy here. So I'm going to say, note that this is a scalar, right? We've been dealing with vectors a lot recently, so hopefully this is sort of a breath of fresh air, because in many ways scalars are nicer to deal with. And it has dimensions, so let's just do the dimensional analysis here. Remember, well, let me write this, 1/2 mv squared. 1/2 has no dimensions, right? It's just a number. The mass, well, that has dimensions of mass. And the velocity squared has dimensions of length squared over time squared. And so this is an energy, right, as we have just said. So we note now that the dimensions of energy will in general be a mass times the length squared, all divided by a time squared. The SI unit for energy is the joule. I don't think I'm supposed to capitalize it, even though it is, or was, somebody's last name. And we can see that, well, if we just put our base units into the dimensional form here, right, we find that 1 joule is defined to be 1 kilogram meter squared per second squared. So let me just fix these italics, because units should not be italicized. And there we go. So this, I want to say, is not horribly complicated. We'll look at an example here right away to just sort of get some practice with this. I don't think that there's really anything more to say about kinetic energy at this time. And you know, that you might be wondering what energy is, and that's kind of a tricky question. I am going to, for the time being, just say that it is a quantity in physics, and other disciplines too, I suppose, that we care about for specific reasons. And one of the reasons is that it allows us to solve for some things that we might be interested in solving for. And we'll see that a lot of the times it's a conserved quantity. Well, I guess it's always conserved, but we have to be careful about how we go about applying that. But we'll get to that later. So let's look at this example, though. You throw a baseball with mass of 0.145 kilograms up into the air with a velocity v0 equals 20 meters per second. We want to find its initial kinetic energy and the kinetic energy it has at its maximum height above the ground. And so let me just fix this. I want to say straight up into the air here, because the way I envision this is that you throw it up and it only has a y component of velocity. So let me just clarify that, or I guess I did. So that's important. Anyway, the kinetic energy as it's leaving your hand is this. It's K equals 1/2 m v naught squared, right? And if you plug the numbers in, you should find, I believe that this is exactly 29 joules. So you can confirm that for yourself. And I mean, that's it, right? That's all that really goes into this calculation here. And then so the other part was we wanted to find its kinetic energy when it's at its maximum height above the ground, right? And so to do this, we recall that at the baseball's maximum height, it's, well, let me just say its velocity is 0 because we're talking about just y velocity, so I don't think I need to specify with a subscript or anything like that. And the kinetic energy is 0. Now, a good question to ask yourself is, where does that energy go, right? And we're not going to answer that right now, but it's something to think about. And we will see in the next lecture what this looks like in more detail. But that's really it for kinetic energy. I should say I specified that this is translational kinetic energy because later on in the class we'll see that if something is spinning about its own axis, right, you could imagine in the baseball example, right, as you throw it, that it's also spinning around as it travels through the air. There will be rotational kinetic energy associated with that, but we will not deal with that right now. We'll come to it later when we start talking about rotational dynamics. Just a little preview of what's to come, I guess. Anyway, that's it, though, for the time being for translational kinetic energy. And until we actually introduce the idea of rotational kinetic energy, whenever I say kinetic energy, you can just assume that it is translational. Incidentally, translational means that it's just moving through space, right, as opposed to rotational, where it's rotating about its own axis. Okay, so let's talk about work then, and this will be a little more involved because I feel that I have to show you a few different ways of writing this quantity that we call work. But let's talk about what it is conceptually first. So conceptually, work is energy transferred to or from an object via the application of a force along a displacement. So the most general definition of work, and this is not going to look pretty, but don't worry, we don't actually have to really use this. But I would feel remiss if I didn't mention it. It's given by taking the integral of a dot product over a path, in essence, right? And this, like I said, it doesn't look pretty, but not to worry because we won't really have need for this. What this implies, though, for one-dimensional situations, and we will use this, not a whole lot, but maybe for a homework problem or two, is that we can define work for the one-dimensional case accordingly, right? And now we've in essence taken this three-dimensional integral here and made it one-dimensional, and this I think is something that we can handle at the level of this class, assuming that the expression for the force, right, is not too crazy. And for the problems that I give you, it won't be, okay? But let's look at the definition for a constant force, because this is the one we're going to use a lot. So let me just say However, for a constant force, this simplifies to, and it just becomes a dot product. So this and this is a vector, but remember that one of the definitions of the dot product is just the magnitude of the first vector times the magnitude of the second vector times the angle between them. So this becomes simply FD cosine theta. And so let me just write what each part of this means. I'm going to say that here F is the magnitude of the force, D is the distance over which it is applied, and theta is the angle between the force vector and the displacement vector. So the iPad is not working for me right now. So what I'll do is I'll just make a crappy drawing using my mouse. Maybe just so you can have an idea of what this looks like. So if I draw, say, a force that looks like this, and then let's say that the displacement of the object to which the force is applied maybe looks something like this, right? And this would be our D vector. Then this angle between them is theta, and that's what we need to usually know to actually calculate work. Not all the time, because we can, remember, we can compute dot products just component by component, but the approach that we'll take sort of depends on how the vector, or how the force and displacement vectors are given to us, right? And so there's that. Let me just clear this. I did look to see if there was a way I could just clear all drawings at once, and I don't believe there is. So enjoy the soothing clicking sound of my mouse. Nope, didn't mean to do that either. Okay. All right. So I want to, of course, talk about the dimensions of work, right? So let me write this down. I'm going to say the dimensions of work are equivalent to the dimensions of a force times a displacement. Now, remember that a force is a mass times an acceleration, right? So for the force, we have mass, and the dimensions of acceleration are length over time squared. And then to account for the displacement, well, that is just going to have dimensions of length. So we find that this works out to be mass times length squared over time squared. And lo and behold, the dimensions of work actually equal the dimensions of kinetic energy. And so we already kind of see that, well, if these two quantities have the same dimensions, then there's a very good chance that we'll be able to use them together, right? And so we'll talk about this in more depth in a little bit here, but just as a hint at what's to come, what this really means is that the dimensions of work are just dimensions of energy, even though I'll put this in words. So we see that the dimensions of work are the same as the dimensions of energy. But oftentimes, we'll write the unit of work, or I should say units of work, to be Newton meters. But it's the same thing, right? As a joule. Okay. I do want to say one more thing about work before we look at this next example here. And what I want to say is that note that because, and this is where one of those properties of trig functions that I mentioned at the very beginning is useful, is that cosine, right, is bounded between -1 and 1. Thus, we can write, you know, a similar expression for the work done by a force on an object, and we see that it will be somewhere in the closed interval between -FD and +FD. So this is just kind of a sanity check, right, for you to maybe perform when you're calculating something. Is the numerical value between these two, let's say, limits, I suppose. Okay, that does it for the definitions involving work. We're going to look at an example here now. And so the example is you and a friend are attempting to push your car out of the mud. If you each apply a force of 500 newtons over a distance d equals 3 meters, and the car moves in the exact direction in which you're pushing, how much work do you do? How much work does your friend do? And what is the total work done by both of you? So the idea here is that you apply a force in a certain direction, right? And it's kind of arbitrary for this example, but the displacement of the car, the object to which you're applying the force, is in the same exact direction. And what this means, right, in terms of the equation, is that theta equals 0. And so let's write this out, though. I want to say, okay, since you're both applying the same force over the same distance, the work done by you, which will be W sub 1, is the same as the work done by your friend, which is W sub 2. And let's fill this in now. We can write its FD and then cosine of 0 degrees, as I mentioned. And cosine of 0 degrees is just 1, right? And so you each apply I don't want to say you apply a work, but the amount of work done in this instance is 1,500 Newton meters, okay? So we could think of this as how much energy you exert, right, when you perform this action. And so that's all well and good. Now let's think about the total work done by the two of you. And so the total work, or net work, right, I'll probably use both phrases interchangeably as we look at this stuff. And it's the sum of the individual works. And so we can write that work, and I'll just put total here, or actually let me write net. I think that's more common. It's just the work that you do plus the work that your friend does, and we see that this should be 3,000 Newton meters, right? So just double what we had for parts A and B. Okay, I think that's pretty much it for this example. Maybe I will just make a quick sketch of the situation, and it might be a little crowded because, well, you'll see why, but it's like, you know, imagine that the direction that you're applying the force in is like this, right? This is your F. Well, the displacement is going to be represented by this black arrow I'm drawing, and that might look maybe like this, right? And these are supposed to be straight lines. It's just hard to do with the mouse. But I think you can see that what I'm trying to say is the angle between these two vectors is 0. And that's indeed what we used here. So it's useful to draw sketches when you're thinking about work, even though work itself is a scalar, right? Because it is calculated using two things that are vectors. Let me just clear that out. Okay, cool. So let's then look at another example. And this one is about a mass tied to a string, right? I need to stop drawing and write. There we go. Okay, so you tie a string to a mass m, which is 15 kilograms, that is at rest on the floor. If you lift it straight up to a height of 0.8 meters at constant velocity, what is the work done by the tension force? What is the work done by the gravitational force? And what is the net work done on the mass? So the tension force is not so bad. What I would like to do is draw the free body diagram here, just so we're all 100% clear on what's happening. So this is my mass. I have the gravitational force pointing downward, right? Looks kind of like a Y, but it's supposed to be a G. And we'll have a tension force pointing up, because tension is the force that we associate with strings and cords and cables and all that, right? So this is sort of a picture, this is the free body diagram. And our Y direction would be, in this case, just pointing straight up in the same direction as the tension force. So, okay, with the picture out of the way, let's see here. Well, actually, I should probably draw the displacement too, just so we all see that. And in this case, the displacement might look something like this, maybe. And we see then, right, that the angle that the tension force vector makes with the displacement vector is 0 degrees, whereas the angle that the gravitational force vector makes with the displacement vector is 180 degrees, okay? So I'm going to clear that, and then we'll actually solve the problem here. Okay. There we go. So let's say from the free body diagram, we see that the magnitude of the tension force just equals the magnitude of the gravitational force. And this is because, right, we're lifting this thing up at constant velocity, and the words constant velocity are another way of saying A equals 0. So the work done by the tension force is this. I'll call it W sub T, and it's going to be the tension force times the height times cosine, and remember we said that that angle was 0 degrees, right? So this just works out to be TH, and then remembering that T is just mg, it works out to be mgh. And for you numbers people out there, actually, in this case, I actually wanted to calculate the numbers too, because we'll see something interesting here when we do. This is just going to be approximately 118 newtons. Oh, sorry, Newton meters, right? Be careful with units. Okay, so then let's look at the work done by the gravitational force. and I will write this as W sub g. Now this will be the gravitational force times the magnitude of the displacement vector, and then we have to tack on cosine of 180 degrees here. Now cosine of 180 degrees is -1, so this works out to be negative mgh, right? And I suppose I don't even have to put the numerical value in here, but I'm going to, and we see that this is negative 118 Newton meters. So the network, right, is just the sum of the work done by tension and the work done by the gravitational force. And this is 0. And so that's kind of interesting, right? Because, you know, if nothing else, maybe it sort of runs counter to your ideas about what work means. Maybe your sort of colloquial, I guess is the word that I'm looking for, right? Ideas of about what work is. But in this case, you know, it might seem kind of weird that, hey, you know, you definitely applied a force, but the net work done on this thing is still 0. And we will come back to this later. Well, we're actually going to just come back to it right now in essence. And the thing that I want to talk about next is what I call the work energy theorem. I think people usually call it the work kinetic energy theorem, but that's like, I don't know, it's a lot of words to say. So I'll just call it the work energy theorem, and hopefully you can remember that I'm referring to what the textbook probably calls the work kinetic energy theorem. Same thing. So what I want to say is that the previous example suggests that perhaps there's a relationship between the network done on an object and its changing kinetic energy. So let's investigate this. Now, coming back to the example, right, just by hypothesis, the changing kinetic energy of this thing is 0, right, because we said we're lifting it at constant velocity. And so that means the kinetic energy at the bottom of its path is the same as the kinetic energy at the top of its path, right? And so we might be thinking, well, hey, maybe there's some relationship between the network done on the object and the changing kinetic energy, because in this example, both of those things were 0, right? And indeed there is. I wouldn't be saying this if there was not, right? So let's derive the work energy theorem. I'm not going to state it just yet. I'm going to derive it, and then we will have it stated after the derivation is complete. So what I want to do is we want to take the time derivative of the expression for kinetic energy. But before we do that, let's just get a little mathematical tidbit out of the way. So I'm going to say, but first, note that from the definition of the dot product, and this is kind of a lot to write, so I'm going to just copy and paste it from my notes here, but I'll try to remember to give you some time to copy it down, is that if we take the dot product of a vector with itself, we just end up finding the magnitude of the vector squared is the result, right? And so in this case, v dot v, right, and I did it in 3 dimensions for full generality, even though we will mostly limit ourselves to 2-dimensional velocity vectors. This works out to just be the x component squared plus the y component squared plus the z component squared. Now, remember from the three-dimensional analog of the Pythagorean theorem that this is just the magnitude of the vector squared, right? So that's kind of interesting, and it's a result that we'll need. So let me say this then, thus, and now what we're going to do is take the time derivative of the expression for kinetic energy. So remember that was just 1/2 mv squared, but we have just demonstrated that we could write it like this. And what I'm about to do here is not super important for your ability to apply the work energy theorem, but it's just part of the derivation. So it's okay if you don't follow it completely. We just kind of need the result here. But what happens is, if I apply the product rule from differential calculus to this quantity in here, this works for the dot product. We just write v dot, right, where v dot is the time derivative of v, and then over here we have plus v dot v, right? And this, I'll write this out. But remember that the order in which we take a dot product doesn't matter. And so what we find is that this, let's see here, oops. No, okay, I wanted to copy this. That's how I have it written. This just works out to be 1/2 m, and then what we find is 2, geez, I'm struggling, guys, v dot v, right? And so we see that the 1/2 in front cancels with the 2 inside the square brackets there, and this works out to just be, let me copy and paste this, but it's just going to be m v dot v. Like that, okay? And we want to remember that v dot is just r double dot, which is a, right? So remember that this, because remember we said velocity is the first time derivative of position, and acceleration is the second time derivative of position. So what we can do is we can substitute in a for v dot, right? And then we find that the time derivative of kinetic energy is ma dot v. You probably see where this is going. But ma is just the net force on the object, right? So we can substitute F in for that. Like this. Okay, we're almost there. Now we're going to do something that makes, or that's going to make the mathematicians angry, but you know what? Too bad for them, we're doing it. So what I want to do is I want to change the notation a little bit. And I'm going to write this derivative, this time derivative, as the change in the kinetic energy over the change in time, right? And this now equals, we're going to keep the force in there like that. And we can write the velocity as the change in the position vector over the change in time. And we find that the change in kinetic energy is given by F dot R. But this on the right-hand side here, this is just the work done on the object, right? Remember that we wrote it differently. We wrote it as f dot d, but you know it doesn't matter what we call it, right? It's the same quantity physically. And so what this allows us to say is that the change in kinetic energy of an object equals the net work done on the object. And this is a very powerful, useful result. And just to remind you, this is called the work energy theorem, right? So the change in kinetic energy is equal to the net work done on an object. Cool. Okay, let's look at an example then here. So this example says you push a box of mass m equals 50 kilograms, which is initially at rest along the floor in a straight line for a distance d equals 3 meters. If the coefficient of kinetic friction between the floor and the chair is mu sub k equals 0.4, and you apply a force of 300 newtons, what is the box's speed after it has moved 3 meters? So this is just tailor-made for the work energy theorem, right? So I should maybe just make a quick sketch here because that's a good habit, right? So if this is my mass, what we will find is you apply some force that looks like this, let's say in the positive x direction, and we know, right, from the nature of friction that friction will oppose the motion or the intended motion of an object, and so the friction force is going to point to the left like that. And then I also would like to draw in the displacement vector, and I'll draw that up here. It should look maybe something like this, right? And so this is like a little sketch of what's happening. And you know, I didn't draw in the gravitational force or the normal force, even though they're there, because those will both be at 90-degree angles to the displacement vector, right? And remember that cosine of 90 degrees is 0. So there's no work associated with the normal force or the gravitational force in this case. It's just the applied force and the friction force. So let me clear that. Cool. And so now we'll actually write out the calculation here. So the work from the oops, wrong box. Okay. Let me try that. There we go. Okay, so the work from the force you apply is, and we'll write this as W sub big F. This is just going to be FD cosine, and we're going to put 0 degrees in here. So again, cosine of 0 degrees is just 1, so it works out to be FD. Now, thinking back to what we know about friction, right? The friction force is given by F, I'll just call it F with no subscript, is mu sub k times the normal force. And if we had drawn out the full free body diagram, I think we would have seen pretty quickly that the normal force is just equal to the gravitational force in magnitude, right? So this becomes mu sub k mg. And so the work done by friction is, and I'll call this W sub lowercase f, it's going to be the friction force times the displacement times cosine of 180 degrees. So remember that cosine of 180 degrees is -1, so we're going to pick up a negative sign here. And we see that this, once we've substituted everything in, works out to be negative mu sub k mg d, right? Then the network is just going to be the sum of the work that you do plus the work done by friction, right? And substituting in this, we find it's Fd minus mu sub k mgd. And we can, you know, clean this up a little bit. We can just factor out the d, right, and get F minus mu sub k mg inside the parentheses times d. So we're halfway there, right, because we have the work done. Now we just need to fill in the other part of the equation associated with the work energy theorem, right? And remember that that has to do with the change in kinetic energy. So let me say this, while the change in kinetic energy is now delta K equals 1/2 m v squared minus 1/2 m the initial squared, right? But we said in the problem statement that it's initially at rest. So this is just 0 squared. And so the change in kinetic energy is simply the final kinetic energy. Then, let's see here. Equating the network done on the box with its change in kinetic energy, we obtain, and I'm going to copy and paste this, for the, for the speed, right, we find that this is what you should find symbolically and numerically. It should be about 3.5 meters per second. And so the work energy theorem, as I said, is very powerful and useful. And we will pretty much milk it for all it's worth on next week's homework assignment. Okay, that's all good. I think that I've discussed everything that I want to. So let's move on, I guess, to the last example here then. And what we want to do is we want to apply the work energy theorem to a mass that follows the distance h to solve for its speed right before it hits the ground. And we already know the answer, right? Because we did this in kinematics. This was just free fall. But now we can do it another way, and we damn well better find that we get the same answer, right? So let's go through and do this and see if we do. So let me make a sketch here too for this one. And it will be relatively simple, right? Because we have a mass and it's in free fall, right? So the only force acting on it is the gravitational force, like so. Okay, and then if we want to draw in the displacement vector, that might look something like this. So we see, right, that the angle between the gravitational force vector and the displacement vector in this case is 0. And, you know, as we've already stated, cosine of 0 is 1. So I'm going to calculate this a different way. I'm going to do it using the unit vector notation, just so you can see this done sort of in different ways, right? Actually, I'm going to do it as an ordered pair, not with unit vectors. So let me clear that. Okay, so here, the gravitational force is in the same direction as the displacement vector, right? Which we could call, let's call it h, the vector. And if we want to write this as an ordered pair, it just works out to be this. As we saw from our sketch, right? So the work done by the gravitational force here then is going to be the gravitational force written as a vector, right, is just going to be 0, negative mg, and then we dot this with 0, negative h. Let me fill this in. Yeah, let me just fill this in like this. I'm going to say that just so hopefully this is all completely clear. And we see that because of the double negative, right, we end up finding that the work done by the gravitational force in this case is just positive mgh, right, where this is a positive number. And that is a characteristic of instances where we only have one force acting on an object and the force vector is collinear with the displacement vector, right? We should always find positive work done in cases like that. So from the kinetic, or from the work energy theorem, we have that the net work, right, which in this case is just the work done by the gravitational force because there are no other forces acting on an object in free fall, is this, which we found to be mgh, and I should have said falls starting from rest. So let me just put that in there. Though I think that we probably all interpreted it that way, but I just want to make sure that I'm being clear. So we find that the change in kinetic energy is just 1/2 m v sub y squared, because remember, it's starting at rest, right? It's dropped from some height h, and so the initial kinetic energy is 0. And the point is then that for the velocity, or the speed I should say, that it should end up working out after you do the algebra to just be the square root of 2 gh, right? And this is the same thing that we found from kinematics. And so that's encouraging, right? Because we would hope that physics is consistent. And, well, it is, right? So, I mean, I wouldn't be doing my PhD in it if it wasn't. Anyway, okay, so that's it for this lecture. It didn't go for too long, but I think we covered a lot of ground, and you will get some practice working with these ideas on the next homework assignment, and I will be talking more about work in energy, mostly energy, in the next lecture. So I will see you then.